Hi, this is Kevin Trainer. Welcome to my lecture on Chapter 8 of the Hoffer book. Chapter 8 is called Structuring System Data Requirements and primarily has to do with what we call conceptual data modeling. And conceptual data modeling in our course is going to be broken up into two units. The first one is one I'm going to be talking about primarily in this lecture. It has to do with identifying the data of interest in our problem space. Okay, and kind of understanding the different terms we've identified and getting ready to create an entity relationship diagram. So the second part is actually going to be creating entity relationship diagrams, which is pretty much the standard way to express a conceptual data model. Okay, so Chapter 8 really addresses all those issues, and I'm going to go through it here, and it'll probably serve us for both purposes. But the thing to remember is we're going to concentrate first, as our first goal, on identifying the data items that are going to make up the data model and figure out the role that we think each of them is going to play. Okay? Okay. So this process we have is called conceptual data modeling. It's creating a detailed model that captures the overall structure of the data in an organization. In this case, this isn't a conceptual data model for an organization, but for an application. Okay, and it's a more general model than one that we would actually implement in a relational database management system. So this is a start to designing a database for a relational database modeling system, but we're not going to go all the way to designing the nitty-gritty of the relational tables and their indexes and all those kinds of things, and their constraints and all of that kind of stuff. Where are we? Where we're in analysis, if we're looking at the general parts of this systems development life cycle, we're well past planning. We're doing analysis. Having looked at the processing requirements of our system using use cases and to a smaller extent with context diagrams, now we're ready to focus on the more data-oriented requirements. So that's what we've gone on to now. Let's see, our authors have a kind of a point of view about conceptual data modeling. And here's what they have to say. They would have you develop a data model for the current system, develop a new conceptual data model that includes all the requirements of the new system, and then find a way to put that information into some kind of a repository and all that kind of stuff. Now this is probably because our authors have been very much influenced by the methodology that accompanied data flow diagramming, structured analysis and design. And structured analysis and design really broke things up into four parts. And the first thing that you did is you tried to come up with a model of the existing system. Well, structured analysis and design had people working on analysis and design forever. I've got a couple of funny stories about that. So In our data modeling, we're going to be trying to come up with a data model for the new system, the current system that we envision. Okay, so it's going to have certainly will have the elements of an existing system, either an automated one or a manual one. But we're just going to jump right to doing the data model for our target system. So typically the deliverable and outcome of a conceptual data modeling process is either an entity relationship diagram or a UML class diagram. And I've used both. Despite the fact that UML diagrams are kind of the cool tool of the day, entity relationship diagrams, which are very similar in a lot of ways to UML class diagrams, are still the most popular way to create and document a data model. So that's what we're going to use. And in that kind of a model, we document entities, categories of data, relationships, attributes that are associated with the entities, kind of data items. And we're also going to talk about important instances. Okay? Our authors would like to think that we ought to use some data modeling software, and they've been very much influenced by kind of higher end data modeling software, which kind of combines a repository for the information about your data model and a way to diagram it at the same time. The tool that we're going to be using for our entity relationship diagram, Visio 2016, is a lighter weight kind of tool. It doesn't do as much sort of analysis and checking of the model and that kind of stuff. It's more of a drawing tool. And I think as beginners at this kind of work, this is just the tool for us. Okay. So even though in our assignments for the current unit, we're not going to be drawing entity relationship diagrams yet, that's the end goal. That's how we're going to express our final answer for our conceptual data model. Okay? So because of that, it's important for us to understand what a conceptual data model looks like, because we're going to have to generate enough information in our current unit to feed that process. Okay, the skill that I'm going to have you doing as your skills practice for this unit is something we call the rag bag exercise. And it's where we identify all the terms that are going to go onto the conceptual data model. Okay, so we kind of break it up into two parts. We identify the terms, we kind of collect them up into how we think they're going to be represented in the diagram, and then the drawing of the diagram and the improving of it and those kind of things is going to be a second skill that we're going to deal with in the next unit. Okay? So what do we have here? Well, we have a sample conceptual data model, and let's talk about what we have. Let's look at the top half of the slide. Okay. The big kind of things in our problem space, according to this conceptual data model, is we're interested in suppliers and customers and their orders and the products that are on those orders, and the items that make up those products, and the shipment of those items, and the supplier that those things are are shipped from. Okay? Now that's a pretty ambitious system. So what do? Well, we try to come up with the major conceptual things that we're tracking. These are either people or things or organizations, the major ideas, okay? And we call these entities or entity types. So the entity types here in our problem are supplier, shipment, item, customer, order, and product. Okay? Well, how do we know that? Well, we know that through thinking about our problem in a kind of a creative way. Also, it kind of helps us to think about how other people have taken this kind of problem and turned it into a data model. Before the chapter's out, we're going to talk about standard data models. So you could go and kind of look at, well, how do people do a model for this kind of business? And you could actually go out and find a conceptual data model for this kind of enterprise. And you could say, yeah, when you look at it this way, when you use these as the entity types, this works pretty well. So in the diagram, these rectangles represent entity types, types of things or persons or concepts in our problem space. Okay, so if the rectangles are entity types, what are the lines that join the rectangles? Well, these are relationship types. Okay, so what's the relationship between a customer and an order? Well, a customer submits an order, or you can look at it from the other way. You can say an order is submitted by a customer. So these two names are just the same relationship looked at in different directions. Okay. In the diagram that we see here, we're actually documenting the name of the relationship as appropriate from each direction. When we get to the diagramming that we're going to do in the next unit, you're going to see that we're going to do it. We're going to pick a name that is suitable in one of the directions, so that we don't have two names for every relationship. Okay, and we're going to know that we could come up with a corresponding name from the other direction, but we just don't want two times the quantity of names hanging around. Okay, so this looks good. So what else do we need to know about the relationships between these things? Well, there's also this question of what we call how many of one is associated with the other. Now we call these cardinalities. Cardinalities as in cardinal numbers, first, second, third, fourth, fifth. Okay, how many? So here's how you read this. If you look at customer, here's what I'd like to think. I'd like to think that I'm kind of like standing on the diagram. So I walk onto the diagram. I walk onto customer, and I'm looking across the way at order. And the one that I'm standing on right now, I'm always saying one customer is associated with how many orders. And the way to read this, circle and is spreading, we call this a crow's foot, is 0 to many. So a customer is associated with, go over and read the other end of the line, 0 to many orders. So they're going to say, okay, let's look at that relationship in the other direction. So I'm standing on order. One order is associated with how many customers? Well, one and only one customer. Because typically we're not going to take an order for more than one customer. We're going to do individual deals with each of the customers. Okay, and we would like to sell more than one order to a customer. And we might have a customer there are some people who say, well, if we don't have an order from you, you're not a customer. Okay, so they might say, instead of 0 to many, they might have used what we see down here in the relationship between item and product, 1 to many. That's a line in a crow's foot. Well, it kind of depends, right? Some people will record an organization that they're working with as a customer, even if they're just a customer prospect. The other thing that can happen is that you may have a database in which you're keeping orders only for the year, and at the end of the year you put them in some kind of a history part of the database, such that you might have a customer that you're tracking that doesn't have any orders this year. So they might have 0 order here, but they might be an existing customer from some kind of a prior period. So I can see the argument for 0 to many. Okay, so let's look. The relationship between order and product is order requests product. I typically would say that it includes a product. And then here we would say a product is requested on an order. Okay, so again, we're using 2 names here in the designs that we're going to be doing, and again, we're going to be doing that next week. We're going to pick one of the names, whichever name we think is kind of appropriate for our point of view as the analyst. Okay, probably either this or that, but not both. Okay, so let's look at the cardinalities here. If I'm standing on a product, one product is associated with how many orders? Well, 0 to many. I could have 0 because I could have a product that we're carrying at our company. We haven't sold any yet, or we haven't sold any in the current year, so that would be 0. On the other hand, I might have just 1 or 2 or 5. I hope I have a lot because I'd like to sell a lot of things. So 0 to many makes a lot of sense to me. If I look the other way, if I'm standing on order and I look across the other end of the line, 1 order is associated with 1 to many products. If I don't have at least 1 product, I don't really have a proper order, right? Are we going to get an order for nothing? No, probably not. You probably don't have a proper order until you have at least 1 product. And then, of course, you'd like to have many products on the order because we like to sell a lot of things. Okay, so let's look at this. A lot of times, organizations will not differentiate between items and products, right? They'll think of them as the same thing. Here, we're saying that these items make up a product. So a product could maybe be an assortment of items, I guess. So a product it's kind of funny. I'm thinking, yeah, product uses item, and that item is used in a product. Okay. So it's possible if you have a product, is it possible, let's just stand on top of here. I'm 1 product. I can be used in, I can use 1 to many items. Yeah. Okay. I'm 1 item. I can be used in 1 to many products. I think they've got the names kind of reversed here. Now we have a relationship between supplier and item. So in this world, okay, we can get items from more than one supplier. Now, this is true in some businesses, but not that many. To the extent that we have an item, like, you know, a particular screwdriver that we're trying to sell, we probably only buy that item from one supplier, that exact item. We might have other similar items, but they probably have different item codes. Okay, so this idea that one item could be supplied by one to many suppliers, that's maybe a bad idea. Okay, but certainly one supplier this supplies zero to many items. Again, should it be zero to many or one to many? You have to ask yourselves, are they a supplier if they're not supplying anything? Right? So you may want to say, oh, yeah, isn't that one to many items? And then here we're tracking the shipments of these things that are coming from the suppliers. So these are kind of these are the parts. These are the big parts of the conceptual data modeling. Identifying the entity types, okay, identifying the relationship types, figuring out the cardinalities of the relationships. Those are a lot of things that we can do. So these rectangles, when we're talking about these loosely, kind of like the guys hanging around the car shop, right? And let's say we're a bunch of guys who work on cars, and we have a kind of informal way that we talk about things. Okay. We might say, well, a certain thing is a car. The Mustang is a great car. Well, is that really a car that we're talking about, or is that a model of a car, right? Or the sedan is a good car. So a lot of times when we speak, we speak kind of informally, okay? Now, these entity things are supposed to be types, right? So the supplier is a type of thing, okay? And then we're going to have instances of suppliers. Joe's screwdrivers, Harry's widgets. Okay, so type and instance. Okay, these relationships are actually between an instance of the supplier and an instance of item. So there are really instances of the entities, and there are instances of the relationships. An instance of the relationship would be the relationship between Harry's screwdrivers and the large red screwdriver that we order from Harry's. Okay? So this line really represents a type of relationship, not an individual relationship between an individual supplier and an individual item. So what's interesting is when we talk about things, these things in the rectangles are officially called entity types, although you'll hear people calling them entities, and I will too. These things that are the lines with the little notations on them, they're officially called relationship types. But you'll see us calling them relationships. Okay, so the diagram really deals in types of things. We don't really show the individual instances on the diagram. Okay, now let's talk about these cardinalities and how you read these things. 2 lines, one and only one. They called it a mandatory one. A 0 and a 1, a circle and a 1. 0 to 1. Mandatory many. They call this one-to-many. Optional of many, zero-to-many. Okay, I'd like to not use these phrases that they've put here, though I think they're descriptive. I like to call this one and only one, zero to one, one to many, zero to many. So we can have a lot of interesting kind of cardinalities, on our relationship. Generally speaking, the supplier to the shipment is one to many. Generally speaking, the rest of these are many to many. Well, that's not true. We have customer is one to many with orders. Okay, so it turns out that before we get done with data modeling, we're going to find out that these many to many relationships are not really possible to represent directly in relational databases. And we're going to learn some tricks. So between next week, when we express our conceptual data model, which can have many to manys, and the unit after, the week after, where we do a logical data model in which we get ready to have a data model for a relational database, we're going to have to solve the problem of not being able to do many to manys directly in relational databases. And there's a little trick that we're going to learn, but that's 2 weeks away. Okay. So how do you go about gathering the information for conceptual data models? Well, here's what I have you doing. I have you doing a brainstorming exercise. Okay, and when you do the exercise, you'll be doing it on your own. So it'll be a one-person brainstorming exercise. This is one of the two approaches that we have here. So some people think that you might want to take a top-down approach. And so you get an intimate understanding of the business and then you describe it. Or you can take a bottom-up approach, which is you review a bunch of specifications and business documents and all those kinds of things. And then you document that and you turn that into a data model. Ours is probably closer to top-down. Okay, what we're going to try to do is we're going to try to understand the problem at hand and brainstorm about it. So it's probably more top-down than bottom-up. So what kind of questions do you ask yourself when you do this? What are the subjects or the objects of the business? What kind of things are there in our problem space? Okay, those are the things that are going to become the entities. Okay, what are the characteristics that these have? And we're going to find out that these things, or we're going to call them attributes, or pieces of data that are associated with the entity type. The values for the attributes are going to be different for each instance of the entity, okay? And we're going to learn how to represent the attributes in a slide or two. We're also going to be looking for identifiers, or what, when we get to relational databases, we'll call the primary key. Which attributes or data items identify the instances uniquely? Okay, they're going to turn out to be what we call primary keys. There's some things like secondary keys, all that kind of stuff. I'm not going to worry too much about slide 12 for right now. Are all the instances of each object the same? Do we have any supertypes or subtypes or aggregations. The approach that we're going to take to data modeling is we're not going to worry about supertypes and subtypes and aggregations. We're going to take a pretty simple approach to data modeling. So we're not going to worry about that. We are going to worry about relationships. We are going to worry about cardinalities. One of the things that they mention here in slide 13 is events. Okay, well, why are we worried about events? Well, what we're trying to do is we're trying to come up with a data model that can record information about the world that we care about. Okay, so first of all, we have to have a way to describe all the different information that we care about. And then we're going to be kind of interested in what events happen in our world in which those values are going to change, because we're going to want to capture those events in order to keep our data up to date. So we've already seen the beginning of an entity relationship model. So what we've really seen is the beginning of an entity relationship diagram, which is a graphical way to represent an entity relationship model. Okay. The entity relationship model is expressed in terms of the data entities in the business environment, the relationships or associations amongst those entities, and attributes or properties of both the entities and their relationships. So let's go back and revisit what we mean by entities. Well, entity is a general word for things that we care about. Persons, places, objects, events, concepts that are in the environment that we care about. We talk about entity types because we want to distinguish between entity types and entity instances. So, for instance, an entity type would be a product. An entity instance would be a particular product. What's kind of interesting here is that the data modeling that we do is all geared toward eventually creating a design for a relational database. So in a conceptual data model, an entity type is one of those rectangular blocks. And an entity instance is just some idea that we have of something that would be an instance of that entity type. When you get all the way down to something as concrete as a relational database, the entity types get turned into relational tables, and the entity instances get turned into rows in the relational tables. So that's where we're headed, and that's how these ideas are supposed to propel us along. Here's the basic ER notation. Okay. There are lots of versions of it, and there are lots of diagrammers. But generally speaking, entity types are in rectangles. Okay. The rectangles that we're going to draw, we're just going to use rectangles for any kind of entity that we have. We're eventually going to talk about associative entities. We may talk about strong entities and weak entities. But in the diagrammer that we're going to use, they're all going to come out looking the same. Okay, they're going to be rectangles. In the diagrammer, we typically, in the early stages of conceptual data modeling, we don't worry about the data fields that are the attributes of each entity type. We just worry about the entity type name, and we do a diagram like we saw a couple of slides ago, where we have customer and order and item and product and those kinds of things. Eventually, though, we get more detailed. We say, okay, if we have the entities right, and if we have the relationships right, we also have to know what these attributes are. What are the data items? So this type here is the way that we express what the attributes are. And certain attributes have a special characteristic. They make up an identifier or key. Those are typically attributes whose value is unique to a particular instance. A product number, an employee ID, that kind of stuff. Relationships between entities we saw before. We saw a lot that were binary. There's a relationship between two entity types, okay, and the two being bi or binary, okay. There are some situations where an entity type has a relationship with itself. And two really classic situations like this. One is where we have a group of employees and we want to know who is the manager of whom. Okay, so one instance of employee is going to point to another instance of employee who's their supervisor or their manager. Another situation that we have with this, we have an application in manufacturing called Bill of Materials, or BOM, where we're trying to account for all the parts that we use in our organization, and some parts are made up of other parts. So we have an entity type called part, okay, and a part can point to another part that it's a subpart of. Okay, it's just like having a manager, having an assembly that you're part of. So these unary associations are for tricky applications like who's your manager or what are you a subpart of, where different instances of the same entity type are going to be pointing to other instances of the same entity type. Typically, we're pointing at instances of other entity types. You can have three-way relationships. You can have four-way relationships. In the kinds of data stores that we're going to be using in our career, things like relational databases, or the ones that we're concerned with at this point, we cannot directly express three-way or four-way or five-way relationships. They're also very hard to understand. Okay, and it turns out that anything above a two-way relationship can be restated as a series of two-way relationships. So it's interesting to think of the theory of a three-way or ternary relationship, but it's not something that I'm going to recommend that you do in practice. I'm going to recommend that you either have binary or unary relationships. And then, of course, we have the cardinalities down here again. Okay, and the way that I read these again, 1 to 1, 1 to many, 0 to 1, 0 to many. Okay, and this tree-like thing is called a crow's foot because it looks like a bird's foot. And so this kind of notation is called crow's foot notation. So we're kind of particular about the way that we come up with this stuff when we're doing conceptual data modeling. For instance, when we're trying to come up with the name of an entity type, we want it to be a singular noun. So we want it to be product, not products. One of the complaints that I've had about some of the database books is that they show database tables with a plural name. And the problem is that we're eventually going to tell you that you're going to want to turn your entity types into tables in a relational database. And I'd like you to use the same name that you used in your conceptual data model. So if it was a customer in your conceptual data model, the customer entity type, well, I'd like it to turn into a customer's table. Sorry, I said the exact opposite of what I meant. Customer table, not customers. So singular noun, it should be descriptive and specific to the organization, and it should be concise. An event entity type should be named for the result of the event, not the activity or process of the event. So, one of the cases that we work with a lot in this course is the iSchool web store, in which case we're going to pick the items that are on an order, and we're going to ship it. And at least in my data model, I track those things. So I want to represent the result of those events that happen. Okay. We're not going to go into all the documentation that they talk about within the textbook. They want to have an entity type definition, blah, blah, blah. I think we're going to be just fine with the name of the entity type and a list of the attributes and accounting for what the relationships are. For some entity types, the definition must specify when an instance might change into an instance of another entity type and what histories to be kept about entity instances. Well, these are two interesting ideas. History, I think, is a real good idea. For instance, are we going to keep every order that we've ever had in our data model as an order, or our order is going to be the current orders or the recent orders, and are we also going to have some kind of order history, a place where orders go to be referred to but not hanging around to clock things up? So that's an interesting question. When an instance of one type might turn into an instance of another type, this, I think, is a very bad idea. And one that I kind of want to knock dead. So, for instance, when you come up with entity types, whether something is an entity type or not should be pretty much a permanent thing. Okay, so for instance, let's say we have the person entity type. Okay, well that's pretty stable. I mean, you get born, you're a person, then you die. You do have the question is, are you going to consider people persons after they're dead? They just say are persons that have a date of death. Those kinds of things. But you don't have a person turning into a car, or you don't have a person turning into into an order or an invoice. Okay. Now, some people will try to do too much with entity type. Okay, and they'll do. Here's a problem I've seen people get into with it a lot. They want to keep track of people's occupations. Okay, and they go, well, let's see. Let's have a lawyer entity type, and let's have a plumber entity type, and let's have an accountant entity type. Okay, that's great, but is it possible for somebody to be a plumber and to become an accountant or a lawyer? Well, they probably don't want the cut in pay, but yeah, it's entirely possible. So you don't want instances changing type. Well, how could you model that in a way where you wouldn't have that problem? Well, how about we model all the people as people, and how about we model all the occupations as occupation? So person and occupation are the type. And why don't we have a relationship between person and or type called something like is engaged in occupation? Okay, so if a person is engaged in the occupation of being a lawyer, then we'll consider them a lawyer. Okay, if they're not engaged in being a lawyer anymore, if we get rid of that relationship, well, then we won't consider them a lawyer anymore. Okay, so there's a way for that relationship to be put in place to say that they're holding themselves out to be a lawyer right now, and for us to take that away or put some dates on that relationship to say that it was true before, but it's no longer true now. Okay, so that's a way to not have to worry about things changing type. Attributes are a big deal, and we're going to be dealing with attributes a lot this week. An attribute is a data item. So it's a named property or characteristic of an entity that is of interest to the organization. Something like a vehicle ID, first name, product name. Okay? These attributes go inside the rectangle on an ER diagram. We're going to see that in a minute. In fact, let's just go take a look. Where are we? Yeah, here we go. So here is an ER diagram. Here's some parts of an ER diagram for a conceptual data model. And in the rectangle, we have in big type, we have the entity type name, and then we have a list of attributes. The underline, it says that it's an identifier or key. Okay? These squiggly braces say that this is a group that repeats. Eventually we'll get rid of repeating groups, but that's what we say right now. Okay? So let's go back to where we were. So an attribute name is a noun, and it should be unique within your, well, it should certainly be unique within your entity type. Okay? I mean, if two things have a first name, well, I'm okay if they're both called first name. If one is one entity type and one is another entity type. To make an attribute name unique and for clarity, each attribute name should follow a standard format. Similar attributes to different entity types should be used, similar but distinguishing names. So what some people will do is on the employee entity, they'll call it employee first name. On the customer contact entity, they'll call it customer contact first name. We're not going to create a data dictionary here where we're gonna put a definition of what all these things are. Things like what the attribute is and possibly why it's important. That's a little too hypothetical for us. We're going to be dealing with things that are pretty clear requirements. So again, do we have the attribute and what is it called? And if we do, then we're going to list it inside the rectangle on our entity relationship diagram. An attribute definition should indicate if a value for the attribute is required or optional. That's kind of a nice thing to identify. Do you have to do that in a conceptual data model? I don't think you need that detail yet. We would certainly, if we got to a physical data model a couple of stages down the road, we'd like to do that. If a value for the attribute may change, well, we generally think the values for attributes can change. Any relationship the attribute has with other attributes. Okay. Okay, then some of the attributes are going to possibly act as keys or identifiers. So I'm going to tell you that an identifier is the right word for conceptual data model, and key is a better word for a relational database model. So the question is an attribute, is this a thing that would, for instance, identify each instance uniquely? Okay. So we talk about candidate keys or candidate identifiers. Okay. And a candidate key is really any attribute that could uniquely identify instances. And the identifier that we pick is the one that we pick as the official one. The classic case of this is, say, for students. Okay, we could use social security number. In fact, that's the thing we collect at the university. On the other hand, we have a student ID number that we prefer to use for security. So they're both candidates to be the identifier or the key, but there's only one that gets selected to be the main identifier, or what eventually becomes in a relational database design, the primary key. So selection rules for an identifier: choose a candidate key that will not change its value. So we want them to be pretty stable. Choose a candidate key that will never be null, which always has a knowable value. Avoid using intelligent keys. Intelligent keys are kind of coding schemes for key values where we take things that we should be recording as attributes for this entity type, and we try to telegraph in the key text some information that should be recorded separately. So those are called intelligent keys. Actually, they're not so intelligent keys, but we don't want to do that. All we want the key value is to do is to be unique. Maybe easy to remember, but certainly be unique. Consider substituting single value surrogate keys for the composite keys. So composite keys are made up of multiple attributes. Okay, a classic case for this is in my data model for the student attendance system, which I'm going to do in my tutorial. You'll see that the key, the identifier for a particular course offering is not just the course number, but it's the semester number, the course number, and the section number taken together. And sometimes what people will do is say, okay, those three things identify an individual, but we just want one key field, so we're going to create a key field. Typically in a relational database, you'll make it an integer, and you'll call that the surrogate key. So it'll become a single field that identifies the row in the data table uniquely, but it has a one-to-one correspondence with a particular combination of the attributes that make up the composite key, something like semester, course number, section ID. Okay. Multi-valued attributes, we do have some things that have multiple values, and this is the thing that we're going to try to capture over the course of our 3 weeks on data modeling. We're going to try to get on this in a reasonable way. What would a multi-valued attribute be? Well, let's say I had employees and I wanted to know what kind of technical skills they had. Could they program in Java? Could they program in Visual Basic? Could they program in JavaScript? Okay. If I wanted to record all the things they're able to program in, I might say that it is multi-valued. So I've got some multi-valued attribute. I've got from 0 to many instances of skill, for instance. Or a repeating group. I might have a set of 2 or more multi-valued attributes I want they're logically related. Maybe I want to identify the dependence that a particular employee has, and I'm going to want to know their name, I'm going to want to know their gender, and maybe I'm going to want to know their social security number because I need those things for insurance. Okay, that repeats, but it's just not one attribute, it's a group of them, a repeating group. We'll see an example of that in a minute. So here we have some good examples of multi-valued things. Here's the conceptual data model for employee, and we've decided employee ID is the identifier. That's why it's underlined. Okay. In our diagrammer, we're going to maybe have to say that it's the primary key in order to show that it's the identifier, even though that's not really a conceptual data modeling term. Here with these curly braces, we're saying that this attribute skill occurs 0 to many times. So this is a multi-valued attribute. Here, under employee, this is other information under employee. Here's a repeating group that describes dependence. Okay. Now, another thing that we can do, and what we usually encourage you to do, is to create a separate entity for the dependent. And this is kind of interesting. If you diagram it like this is called a weak entity, okay? Because part of its identity is not really, you can't just get by with the dependent name. You really have to imagine that this entity has implicitly on it the employee ID as well. So if you want to be able to distinguish all the dependents, you have to have employee ID, dependent name, all of that kind of stuff. So what we usually do with things that repeat is we break them out into separate tables. And this weak entity approach is a classic thing that we do. And we'll be working on that. Other things to do with attributes. Eventually we have to know is it required? Does it have to have a value? Is it optional? Could it be null, not provided? Is it a composite attribute? Are there several related attributes? Is it a derived attribute? An attribute whose value can be computed from related attributes. Eventually in our data model, we're going to say we're not going to store derived attributes. We're just going to store their precursors, and we're going to calculate them every time we need them. With regard to the relationships, a relationship is an association between the instances of one or more entity types that is of interest to the organization. Okay, so we have, when we draw the line on the diagram, that's a relationship type. Okay, the individual instances of those entities that have a relationship to each other, those are relationship instances. Degree is the number of entity types that participate in a relationship. We're only really interested in two. As a practical data modeler, we're going to use the binary relationship to describe most things. And we're going to use that unary relationship to describe kind of fancy things where one entity type has a relationship with itself. And remember, the two instances of that were where we were trying to track who's the manager of, which employee is the manager of which other employee, or what part is a super part of which subpart. Here is a really great case. I don't see a lot of diagrams like this, but this is a really great case where we see instances of relationships. So this is a way to solve that multi-valued attribute problem. We break off. So we have courses that represent skills, or it could be skilled, wouldn't have to be a course. And we have a relationship, in this case, completes for the course. If it were skill, it would be has a skill, okay? And so what we do is that we have instances of the completes relationship that you can track down to see which employees took which course. Okay? Pretty cool. So this is what I mean when I say that completes is a relationship type. And these lines down here that show how the instances are related to each other, those represent the relationship instances, not something we typically show in an entity relationship diagram. The unary relationship is the fancy one where an entity type is related to itself. We call that self-relationship recursive. The binary relationship is just a plain old mom and pop relationship between two entity types. A ternary relationship would be a relationship between three entity types, but there's no reason to draw that because there's no way to represent it in your average data store. So since you can take any higher order relationship, 3, 4, 5, 6, 7, and there's a trick for expressing them as a series of binary relationships, we're only going to be worried about the unary and the binary relationships. So here are some examples of relationships of different degrees. So in the upper left, we see we're able to capture which people are married to whom, with the unary relationship is married to. An employee, we can show which employees are managed by, or which, the way that they do this, which I don't like, is that they're saying which employee manages which employee. I think it's a lot easier to say for a particular employee, the relationship for me is has manager, so you only have to point to one. Team, these are team standings, okay, as in who's in first place, who's in second place, who's in third. So you can express the standings of all the teams with stands after, okay. One to many, a product line contains many products. Here's a one-to-one. An employee is assigned parking space. I'm always suspicious about things that are one-to-one. If we only have one parking space per employee, and we always have one parking space per employee, then why don't we simply just have an attribute on employee for parking space number? Okay. Well, perhaps we have more to say about the parking space. Maybe we need to say, here's when they got the parking space. Here's how long. Here's how long they've committed to it. Here's how much they're paying for it. So you might have things like that, or you might have something like each employee is associated with 0 to 1 parking spaces. So some employees have parking spaces and some don't. Well, that's a good example for that kind of a relationship. But I would have the cardinalities be a little different. But generally speaking, as soon as I see a one-to-one, I get suspicious. And I want you guys to get suspicious too. Many to many, we have a lot of these in conceptual data models. We have many students are registered for many courses. In a conceptual data model, we can draw them just like this. So we can put the crow's foot on both ends, and you can see we have a many to many. We can't represent those directly in relational databases. So when we go 2 more steps down our curriculum and we come up with a logical data model, we're going to have to introduce a trick to make a many-to-many work in a relational database. But for right now, we can just simply draw it just like that, just like registers for. A ternary relationship, I've got 2 words for you. 3 words. Don't do it. Okay? The cardinality we talked about, okay, it's the numbers of which entity type associated with which other entity type. Again, most of the relationships that we have are binary, two entity types. And we have this idea of a minimum and a maximum, okay? So the minimum cardinality is the minimum number of instances of entity B that must be associated, or that may be associated with each instance of entity A, and then the maximum is the maximum. There are some difficult situations in which you're trying to decide whether something should be 0 to many or 1 to many. For instance, if we set up the rules of our database that says, let's say we have a shopping cart for online shopping, and we've got items in the shopping cart, okay? So the person begins to shop, okay? Is it okay for them to have 0 items in the cart? Well, yeah, probably, because it's a common case that you're shopping and you haven't picked any items yet. Okay, that's great. So let's go to orders, okay? Is it typical to have an order without any items on it? Well, no, you typically don't have a proper order that doesn't have any items. But what about when you're building it? Okay. Okay, so when you're building the order, okay, you create the order part, and now you want to add the items part. What does the order look like in the very brief time, maybe milliseconds, between when you create the order part and when you associate the item part? It might be an order without any items. So there are times when you are setting up the rules where you have to distinguish in your mind between uh, what are the rules for, say, an order when it's in its good, fully populated state, as compared to what state might it be in while you're populating it. It's a very narrow set of circumstances, but a lot of times it means the difference between whether you say one and always one, 0 to 1, or 1 to many, 0 to many. Mandatory versus optional cardinalities specifies whether an instance must exist or can be absent. That's just the issue that we were talking about. On an order, you typically always want one item, but that's a proper order that's fully populated. If you're in the process of populating it in the database management system, you don't want to create the order part and then have it go berserk and say, well, I don't have any items for that yet. You go, well, I haven't given them to you yet. Just hold your horses. These are cardinality constraints. So mandatory cardinalities, we have a patient history. Optional one, employee is assigned to project. Employee might not be assigned to any project. Again, think about part A of the slide here, though. Is it possible to have a patient who doesn't have a patient history? Well, no, in some sense, because if we haven't taken their history, they're not a proper patient. But what about if they just walked in for their first visit and they're in the waiting room, and so we put them into the system as a patient, and we haven't taken their history yet? Should we allow 0 patient histories? I think we should. Okay, so that's the issue I was trying to get at. Optional cardinalities. We have a person is going to be married to 0 to 1 person. That's great if you don't have plural marriage. Okay, so these things, people often say, well, how do we figure out what the rules are? Well, we figure out what the rules are by talking to the stakeholders. Okay, and we certainly want the rules to be expressed in a way that are going to serve us for quite some time. So you might ask, for instance, with example C here on this slide, you might ask, are we going to support plural marriage? And they might say, no, as a matter of policy, we're not going to support plural marriage, so we're not going to represent it in the system. Or they might say, well, in this organization, we have some people who believe that they're plurally married, and we want to be able to track that. And so, yes, we want that capability to be there. It's a question of what the requirements are, and you want an eye towards the future. Certainly, you don't want to rely on just the issue, are there any of these right now? Okay, maybe there aren't, but could there be any of these in the future? Well, if we're at least not sure, then we ought not set the rules against them. How do you name the relationships? So relationships are typically named for a verb phrase. Okay. I tend, in my class, you only have to name them in one direction. That keeps you with, and you can pick a name that's appropriate in only one of the two directions. Okay? So, so you might say the relationship between orders and items. An order has an item. An item is on an order. Okay? Pick one of those two. All right? Relationship definition, we're not really filling out a data dictionary, so that's not something that we're going to sweat. A lot of this stuff in 38 is just too much detail for the level of detail we're putting into our data model at this point. Associative entities are really kind of interesting things. This is something that we're going to learn about now, and then we're going to use it more and more as we go from conceptual data model to logical data model. So an associative entity is an entity type that associates the instance of one or more entity types and contains attributes that are peculiar to the relationship between those entities. Some people call this a gerund. So the data modeler chooses to model the relationship as an entity type. So, for instance, remember how I told you that in relational databases, we can't directly model a many-to-many relationship. Well, how do we do that? How do we resolve that? Well, we create an entity to be in the middle, an associative entity. Okay, and these are like three versions of how you do it. Okay, but when do you need an associative entity? Well, when there's a piece of data associated with the relationship. Okay, so let's look at example B. We have a relationship between an employee and a course. That's a many-to-many, right? So how do we tell those relationships apart? Well, they have a certificate number. Those are unique. And they have a date completed, okay? So we wouldn't keep the date completed on either the employee or the course. It really has to do with the relationship between those two. So we create an entity in the middle that associates those two called a certificate, and that's a home for the date completed right there. All right. Now what's interesting is in our next phase, again, this logical data model, which we're not going to get into for 2 weeks. Whenever we have a many-to-many, we're going to have to create an associative entity or an associative table, even if we are not carrying any data on the relationship like date completed. Our motivation for an associative entity in a conceptual data model is when there's a piece of data associated with the relationship. Something like this, a date completed that we see here. And here's a summary. We're not going to worry about supertypes and subtypes. 2 reasons. One, Supertypes and subtypes are not directly implemented in relational databases. And that's really the promised land for us. Most of the applications that we're going to be creating are going to be implemented with relational databases. And so it'd be interesting to learn about supertypes and subtypes, but we're not going to get anywhere good to create supertypes and subtypes and then to get to our logical data model, and then we've got to fiddle around to implement those. So we're not doing that, which means we're not doing 43 either, or 44, or 45, 46. Don't think we want to talk about that too much. Okay, 48 here. This is something we have to talk about. When we think of our model, we have to think of the attributes. We have to think about what valid values are for a typical attribute. And a word that they use in data modeling for that is what's its domain? Okay. If it can it hold any character string? Can it only hold the values small, medium, or large? Okay, so that's the thought. Okay. Triggering operations, those are very much more physical database issues. We're not going to worry about those. So 49, we're not going to worry about. We are going to talk about here this universal data model. Okay. You don't have to invent every data model yourself. If you are trying to come up with a data model for an e-commerce application, it's okay to go out to Google and say and do a search for a data model for an e-commerce application. I'm not going to want you to copy it, piece for piece, but to take inspiration from it, absolutely, right? So, things like manufacturing, banking, e-commerce, brick and mortar retail, services. I mean, there are only so many kinds of things that we do. Libraries, archives. So it makes sense to go see what other people have done. And how can you do it? You can just go to Mr. Google and ask, and you can find a lot of stuff that you can use as the inspiration for the data model that you create. You can find some of these, even certain industry organizations will, part of their industry association is that they'll collaborate on what they consider a good data model for their industry is. And you can find those. That's when you Google these things, you could easily find when you're searching data models that come from some kind of industry organization. And these last couple slides have to do with their Pine Valley furniture case, and we're not really talking about that. So here we are. We're in week 1 of data modeling. Okay. And we've just been through all the stuff that we're going to need for pretty much weeks 1 and 2. Okay? So when you go to look at the assignment for this week, you're going to see that we're having you identify terms, words that go with things and concepts and all that kind of stuff that are going to be part of your data model. We're going to come up with a list of terms, what I call a rag bag of terms. Okay? And we're going to have you sort them. We're going to have you do a brainstorming exercise where you come up with all the terms that you think have to do with their domain. And then we're going to have you sort them into, what's your best guess? Is this an entity type? Is this an attribute? Is this a relationship type? Is this a particular instance? Okay. And so we're going to, in the ragbag exercise, when we're done, we're going to have a list of terms. They're going to be sorted by how we expect to use them in the data model. Okay. We have found, many of us have found, that if you're trying to draw the ER diagram and do the thinking at the same time, you generally do kind of a bad job of both. So what we're trying to do here is, with the ragbag exercise, have you do high quality thinking. We've already sensitized you to what we're going to use this for. Okay, we already have some idea about what this entity relationship diagramming stuff's going to be. But before we go about drawing those and worrying about the exact rules and the diagrammer and all that kind of stuff, let's just get the raw material identified and organized, and have a good set of ideas that we're working from. So that's what you're going to be doing for an assignment this week. It should be fun. It's something that I really enjoy doing, particularly with a group of people. And next week, we're going to go on to actually creating an entity relationship diagram that's going to express our conceptual data model. That's going to use that raw material that we came up with in the ragbag exercise. So off you go. Good luck with this, and I'll see you next time. Bye-bye.